Okay, welcome to this video that is going to demonstrate generating the parent graphs for y equals sine theta and y equals cosine theta. You're probably at the beginning of a unit on graphing transformations of these functions, and as is the expectation when you're using transformations, that you have to be fluent and quick and great with understanding the parent graphs. This is going to show how to generate those parent graphs. Be on the lookout as you move through the unit for the idea of the periodic nature of these graphs, which is something you probably haven't seen before. It's kind of inherent in many of the trig graphs. Okay. This video is going to assume that you have a fluent understanding of the unit circle and the definition of cosine and sine. If you don't, you're going to need to kind of find that elsewhere, but if you're here at this video, we're assuming that you're good there. Also, it's going to have an assumption that you move between degrees and radians pretty fluently, because a couple of the things that I'll show measurements of are done in degrees and a couple are in radians, and you should be able to comprehend that. Just real quickly, a pi radians measurement of an angle is in fact 180 degrees. So from there, you should be able to split up the circle pretty well. All right, so like I said, you have to be able to comprehend the unit circle, and this is just a static drawing of it, but I also have a demo here that will allow for us to be able to pick an angle, such as like 180 degrees, and be able to look at the cosine and sine values as they are generated from just measuring that point. I'll be able to go around the circle decently quickly and be able to generate these values as we build the graph. So I'll start back at 0 here for a second, and then we'll take a look at being able to make the parent graph for the sine function. Let's move my toolbar where I want it. Okay. And we have this on trig paper with pi quarter units for right now. You see that we have a table of values for inputs for theta, and we see that it goes from 0 to 2 pi, which makes sense because that is one trip around the unit circle. Okay, so let's get going and we'll build this whole set of points, and then we'll talk about which ones are really important. Okay, so here we go. Starting at 0 degrees for the sine graph, we see that 0 degrees is going to give us a sine value of 0. And I'll pick up another one here for 45 degrees, which is 0.707. 45 degrees is obviously pi quarters. So I'll get those in there. We'll go 0, 0.707. Let me see next we're dealing with pi halves and 3 pi quarters. Okay, so I'll go back to my demo here. Pi halves is 90 degrees. And we see that the sine value is 1. And then when I go to 3 pi quarters, which is 135 degrees, we see that sine value again is 0.707. So we'll take another look there and go with 1 and 0.707. Okay, so continuing to go around the unit circle, we'll go to 180 degrees, which is pi radians. You see right now I'm just going 45 degree increments or pi quarters. So we see that the sine is 0, and moving forward, we see that now in the third quadrant, sine is negative as we would expect, and it's 0.707 negative. Okay, so we've got 0 here, negative 0.707 here. And when I go to 3 pi halves, which is 270 degrees, we see the sine value is negative 1. And then when I go over to 315 degrees, it's negative 0.707 again. So I'm going to go from negative 1 to negative 0.707. And then 2 pi, it should not be a shock. It's coterminal to 0 degrees. Same for 360, just in the degree units. And we see here that the sine value is, again, 0. So that's all I need to do to generate these values, okay? And I did it in colors here, so you'll be able to see ones that are really critical, okay? So I'll plot all my red ones first, and we'll see how they look. So we've got 0, comma 0, and then we've got pi halves, comma 1, pi, comma 0, 3 pi halves, comma negative 1, and then 2 pi, comma 0. Okay? Now, if you look at that, you might think, okay, I just connect the dots, you would get sort of this picture here. It looks like some, peaked mountaintops upside down, what have you. But as it is the case with any graph, if you want to comprehend its contours better, you should pick more points. And if you notice now when I put in the green points, which are all 0.707 or negative 0.707, you'll see it gives this wave a contour. So for pi quarters, and I know that it's pi quarters here, each increment, because if 2 grids is pi halves, we know that 1 grid is pi quarters. So we see at pi quarters you get 0.707, as well as you get it at 3 pi quarters. And then at 5 pi quarters you get negative 0.707, which, is between negative half and negative 1, so I'm kind of estimating it a little bit. And similarly, for 7 pi quarters, it's negative 0.707. Okay? So, now, that being said, what we want to see here is a nice curve which creates a wave. This is a sine wave, okay? There's some very important things you want to note about it, because later I will talk about what you're committing to memory, okay? And we'll just take a look. The width of the wave goes from 0 to 2 pi, okay? This is called the period. It's the length of one cycle of the wave. Well, what do we mean by one cycle? Well, it's a piece of the graph that you get that in its entirety you see before it starts to repeat. And when it repeats, it just repeats itself. And we'll talk about that in a second here, okay? You see that the maximum value is 1, and the minimum value is negative 1. This is very important for the sine wave. We also see that the output starts at 0 and ends at 0. We also see there's a 0 in the middle, and that's very important when we talk about the sine wave, okay? So now, if we realize that if I just continued to go around the unit circle, because it is a circle, I would get all the same values again on the second trip. Now, a bit of a misnomer here that if I hit 45 again, you could imagine that for a second, but that's actually a trip of 360 and 45. Okay? So 360 and 45 would be, in fact, 405 degrees, or it would be known as 9 pi quarters radians. Okay? Well, if you see with that, you see the sine value is still 0.707. Okay? Then if you could sort of imagine that at 9 pi quarters, which is right here, it's 0.707, you would see now that the graph would just start to repeat. And that's in fact what it does. And that's the periodic nature of the graph. So what I could say here is that this first cycle will repeat, and I'll create a second cycle that is identical to it. I'll do it dotted. And you'll see it's just going to repeat here again with the same exact points, but in this case it's going to go from 2 pi to 4 pi. Okay? So I'll draw another cycle in. Like I said, I'll do it in dotted. So it really is going to look like this. Okay? And there you have it. So this is 2 cycles of the sine graph. Okay? Now, the parent graph is really just to be considered the following part. Okay? And what I'm going to do here is erase here, okay? Move this cycle for a second and take out the greens, okay? So these 5 points are the basic parent function points. It creates this cycle if I sort of connected the dots in an educated fashion. If you notice, it's just the reds. So in terms of what we want to be able to have committed to memory are these 5 points. 0, 0, pi halves 1, pi 0, 3 pi halves negative 1, and 2 pi 0. Now, if you weren't using our fancy schmancy sketchpad demo, you could be able to get those points generated again if you're struggling memorizing them by taking the pi halves increments, which are all the axis values for theta, and be able to look at those. And again, if you're looking at the sine value, it is the y coordinate, and then later when we do the cosine value, it'll be the x coordinate, which I'll do in just a moment. So again, this is one cycle of the sine curve here. The red points are the ones you have to have committed to memory, okay? So I'll actually remove the cycle for a second so you can actually see those. Putting it back, realizing that's what you need to be able to commit to memory. And again, you need to be able to have these input outputs that I have in red in the chart pretty well memorized. Okay? So, that being said now, what we're going to do is take a look at the basic cosine graph. Now, if you notice, I'm still going to use the same input values. Okay? And I'll use my sketchpad demo to go around again. We'll go around for 2 pi. Notice we've got plenty of values here, and then we'll talk about maybe what the critical ones you could commit to memory for that are. Okay? So, we'll do this 2 at a time for the sake of going back and forth. Okay, I'll start at 0 and pi quarters. Okay, first thing I want to do is take out that. I'm going to start at 0 here. And again, I'm going to focus on the x value because that is the definition of the cosine of theta whilst you're in the unit circle. It's the point that intersects the terminal side and is on the circle at the same time. Okay, so we've got the cosine of 0 is 1, and the cosine of 45 or pi quarters is 0.707. These are some pretty famous values here. So you've got 1 and 0.707. Okay? And when I go to pi halves, which is 90 degrees, we see that we have 0. And then when I go to 3 pi quarters in the second quadrant, you would expect the cosine to be negative, and we have negative 0.707. So that's going to give me 0 here and negative 0.707 here. The next 2 values are pi and 5 pi quarters, which are also known as 180 degrees, where I get negative 1, and 225 degrees, where I get negative 0.707. And in the third quadrant, that makes sense that you would think cosine would be negative. Then I'm going to go to 3 pi halves, which is 270 degrees. And I see that I get a 0. And then when I go to 315, I get 0.707, which is positive. And in the fourth quadrant, you should know cosine is positive. So what does that give me here? I've got a value of 0 here, like I said. And then 7 pi quarters was 0.707. And then finishing back up where I started, if you look at the chart here, you see that 0 degrees gives me a value of cosine of 0 being 1, and you are in fact just going to get the same value for 2 pi, which is 360 degrees, because they are coterminal. Okay? So we'll make a graph of that decently quickly, and we'll try and note some things about it. So I'll start at 0, 1 by doing my reds. Pi halves 0, and then I'm going to go pi negative 1, and then I'll get 3 pi halves is 0, and then I'll get 2 pi is 1. Now again, if I just sort of connected the dots there, it would look like a V, which is not appropriate. Sine waves are called waves for a reason, and cosine waves are called waves for a reason. Now you see too, if you add these additional points in, pi quarters 0.707, and then 3 pi quarters negative 0.707, and then 5 pi quarters the same, and 7 pi quarters 0.707, you see that you get, again, more of a contoured wave, which is a pretty neat curve. Now, I'll just use the little smartboard trick of taking that picture and cloning it, because, in fact, I do get that cycle to repeat. So what does that affect? It's really just like copying and pasting. So that would be 2 cycles of the cosine graph. Now, let's take a look at a couple of things here to study. Much like sine, the maximum on cosine is 1, and the minimum is negative 1. Now, this makes sense because you're never being able to give a value bigger than 1 or negative 1 on the unit circle, because you would be outside the circle. Okay? We see that 1 cycle of the graph, I'll just remove the second one for a second, is 2 pi long. And you can see that by taking the measurement from here to here, from the start to the end, and just sliding it down and seeing that it's 2 pi long. Okay? That's really important. It is periodic in nature. Okay? And that means that you get this repetition between 2 pi and 4 pi, which would just mean to go around the cycle again. And now that I have that in there, I'll just kind of demo that for a second. We'll take a look at 7 pi halves, right? You notice that 7 pi halves, comma, 0. So 7 pi halves, if I went back onto my drawing here and actually drew on it, I counted off by pi halves, I would get 1 pi half, 2 pi halves, 3 pi halves, 4 pi halves, 5 pi halves, 6 pi halves, 7 pi halves, okay? And that would allow me to look at this angle per se, and I would be looking at this point here, and I could see that the y value of that point is, the x value of that point is 0. It would be coterminal 270 degrees. So if you notice, it is in fact 0. So let me just undo those for the sake of keeping that neat and tidy. And if I look back here, just like I said, at 7 pi halves, I get 0. So the fact that I use the geometry to create a repetition is not anything but legit, because if you go around the circle multiple times, you just wind up in the same places periodically. Hence, it's a periodic function. So, what do we want to take away from this? I'll take this cycle out, remove this little learning opportunity that I commented on here. I'm going to remove this cycle just for a second, okay? And then I want you to sort of take out the greens. They are there, and then you have to be able to commit these points to memory, okay? Now to do that, you realize that cosine kind of starts at 0, 1, and ends at 2 pi, comma 1. So it's the output is, it's starting at 1 and ending at 1, okay? In the middle of that, you're seeing that the output is negative 1, okay? And in the left quarter of that, you're seeing that the output is in fact 0. And in the right quarter of that, you're seeing that the output is 0 again. Okay? So that means you want to be really familiar with these red points and sort of visualize the green points. Okay? So that is where you are. Knowing that the parent graph is these red points and then connected by the nice contour of that blue graph. Okay? Well, that takes us to this last thing to sort of close this idea out. What are the non-negotiables you need to take away from this for when we talk about these parent functions? Again, This is about using these graphs to create other graphs by doing transformations. So you have to memorize the parent function graphs, okay? You have to memorize the parent function tables. You need to know that the period of each graph is 2 pi, and you need to know that your periodic nature of the functions create repetitive waves known as cycles. One more piece you need here. You need to know that the max for cosine and sine is 1, but it happens in different places, and that the min is -1. When I say this, these are output values, okay? So you need to be able to see those pretty readily when you do this. Okay, so again, everything that's in red here needs to be committed to memory. I could sort of imagine that feels overwhelming, but trust me, it goes very quickly after a couple drawings of this. This one is cosine theta, and back here is sine theta. And again, everything in red on this slide, not misspeak, should be committed to memory as well. Okay? So, just end this up in a second by taking out these green pieces here, like I did on the graph, and leaving you to some memorization. Good luck, enjoy, feel free to share.